All right, guys, we have made it. We're on to Unit 9 here now. So Unit 9 is kind of taking everything, pulling it all together, okay? So we're going to start with just a couple of new things here. The first piece that we wanted to start with is our entropy, okay? So entropy is kind of the degree of randomness or disorder. Okay, of a system. So how much movement those particles have, how many things that we have happening. So if we think about a phase change, right, we can think about maybe a solid going to a liquid, right? It's going to be able, those particles are going to be able to move more. So that's going to increase the entropy. If we go from a liquid to a gas, same idea, right? The particles are able to move around more. It's got more randomness, more disorder. So it's going to increase the entropy. So we increase going from solid to a liquid to a gas. Okay? If we think about chemical changes, right, we maybe are going from a solid to a solid. That's probably not going to change the entropy a whole lot. But if we're going from like a solid to a gas, right, we're going to increase the entropy. So if we are going to more moles of gas, that means that we are going to be increasing the entropy. Kind of there's more space for those gases, okay? Or more particles, okay? And then if we think about our temperature change, same idea as our phase change. As we increase those movements, right, there's more randomness occurring. So our temperature increase causes an increase in entropy. Okay, so if we increase temperature, we generally increase the entropy. Okay, so whenever we are calculating these, we can actually calculate them precisely. So we have standard state entropies. These would be values that would be given to us, and we would be able to calculate the overall entropy for a reaction, right? Same idea as we have done with our delta H, where now we have a delta S, right? H was enthalpy, and S is entropy. So H is enthalpy, S is entropy. But whenever we calculate these, we can actually calculate in the same way, products minus reactants, okay? So sum of the products minus the sum of the reactants, we can subtract the two, and that's going to give us our overall reaction entropy, okay? Now, these two things are what actually kind of control a lot of our reactions, okay? So this has to do with thermodynamic control, okay? So when we have an equilibrium system, right, it's going to be under thermodynamic control, and the enthalpy versus the entropy are really what's going to be controlling things, okay? So what a question that we can kind of start with is, you know, why are we able to do an endothermic reaction, right? An endothermic reaction, we're talking about the enthalpy there. The endothermic, it's absorbing energy from the surroundings. But why does it do that? Because the entropy causes our system to kind of change energy in a positive or in a favorable way, okay? So it's really, right, Gibbs Free Energy that we most often talk about when we talk about, can this occur? Okay? If we're asking, hey, can this reaction occur? We're going to be talking about Gibbs Free Energy, okay? And we often, right, when we're talking about Gibbs Free Energy, we often compare it to the standard states. So let's remember those standard states again, right? We've got our S naught, our H naught, G naught. All of these are talking about our standard states. So standard states, right, 1 molar solution, 1 atmosphere for gas, and then for our solids and our liquids in their pure states. Okay, so pure substances. Uh, pure substances for solids and liquids. Okay, so we have H, we have S, and now we have G, that is Gibbs. Okay, so when we talk about reactions that are under thermodynamic control, we talk about thermodynamically favored reactions, okay, whether it's thermodynamically favored or not. The ones that are thermodynamically favored are essentially going to be releasing energy to the surroundings. So delta G naught is less than 0. Okay, so our Gibbs free energy is going to be negative when we are thermodynamically favored. So again, fortunately, if we're calculating our Gibbs free energy from our known Gibbs energies, we can actually just do, again, products minus reactants. Okay, so we're always going to use that products minus reactants, just as we had done with enthalpy, just as we can do with our entropy. It's really convenient that it's all the same, okay? Each of these equations are on our equation sheet, okay? But then let's also talk about the relationship between our enthalpy, entropy, and Gibbs, right? So if we talk about our Gibbs free energy, it is a relationship between our enthalpy and entropy, okay? So the equation that actually relates them is that delta G naught is delta H minus T delta S, okay? So again, that entropy depends on temperature. It's going to affect that temperature. And so if we have different temperatures, right, if we increase the temperature, we want to increase the entropy, okay? So if we come down here, we can actually kind of summarize everything all right here. If we've got a negative enthalpy, right, it wants to release energy to the surroundings. And if we have a positive entropy, right, we want to increase that entropy. The universe wants to go to an increased entropy. So if we have a negative enthalpy and a positive entropy, it's always going to be favored. We are going to have a thermodynamically favored reaction at all temperatures. If, however, we've got a positive entropy and make sure I get this right, a negative enthalpy and a negative entropy, this gets real confusing, all right? So negative and a negative, the reaction overall is only going to be favored at low temperatures, okay? Because once we get to higher temperatures, that negative number from the S is actually going to force our G to become positive, okay? So our Gibbs can become positive at high temperatures, so then it is no longer thermodynamically favored, okay? Let's talk about that opposite situation. When we have a positive enthalpy, right? This would be an endothermic reaction, okay? So I'm going to write something here. This is exothermic. These two are endothermic, okay? So if we have an endothermic reaction, but we have an increase in entropy, we can actually get the reaction to occur at high temperatures, okay? Our Gibbs energy is going to become negative when we have a large enough, right, positive entropy. If we increase that entropy and we multiply it by a high temperature, we're going to be able to get that endothermic reaction to occur, okay? But finally, if we have an endothermic reaction and a negative entropy value, right? We're decreasing the entropy. Those two things mean that we are never going to get that reaction to be thermodynamically favored, okay? So this table right here, right? If we think about this equation and using this table, right? That's going to kind of summarize a whole bunch of our ideas of what's happening between entropy, enthalpy, and Gibbs, okay? All right, I'm going to pause and then we'll come back in a sec.